Alright, so let's learn how to prove a trig identity. But let's first find out what an identity truly is. So an identity is simply an equation. Say in trig here, the one that we've learned very early is sine square of angle theta plus cosine square of theta equals 1. So this is called an identity. So what is in an identity? It is an equation, it has variables, and it is an identity guarantees that this equation, regardless of what variable we're substituting in, will always be true. The equality will always be true between left side and right hand side expression, regardless of whichever input values we are giving for the variables. So here in trigonometry, we have these identities, and we're going to be proving many other trig identities here. And trigonometry is not the only course where you see the idea of identities. Say, for example, back in algebra, you have seen some identities famously like the a square minus b square. We start out with the difference of two squares, and this is famously known to be the same as the product of a minus b as a difference multiplied with a plus b. So this was an identity we've learned back then in algebra. So the idea, again, an identity has two sides as two expressions and with variables, and the identity guarantees that the two expressions on the left-hand side and the right-hand side are always equal, regardless of what values we're substituting in for the variables. And let's now look at a common misconception about proving an identity here. Let's say back in algebra, there are times that we are asked to prove why the difference of two squares, a square minus b square, will always equals a minus b in product with a plus b. So why is this equality true? The left-hand side, regardless of which variables or values we're giving it, will always equals the right-hand side expression. Why is this always true? The misconception I want to point out is that sometimes we just simply substituting in, let's say, let a equals 2 and b equals 5, and then we're going to start out calculating the left-hand side being the 2 square minus 5 square, consequently giving me a value being, so that's a 4 minus 25, give me a negative 21, and the right hand side, in the meanwhile, using the two same values of a and b that we provided for the right hand side, we're looking at 2 minus 5 in product with 2 plus 5, and that gives me minus 3 times 7, which is also a negative 21. And we stop there and saying, therefore, and once we got to that, we say, therefore, the left-hand side, a square minus b square equals a minus b in product with a plus b. This is a misconception. This is only an example. This is only an example. I have to make it clear here. The work we have done here is only an example. It's not a proof. Because it's only represented, it's the equality here is true based on these two values that we have given for the a and b, but did not represent how it's generally true for all other values. And so similar misconceptions about proving an identity in trigonometry. Let's say we have a sine square of theta plus cosine square of theta equals 1. A lot of time teachers explain in class that, hey, if theta, if we can just let theta equals theta equals the values 2 pi over 3, then the left hand side is going to produce a sine square of 2 pi over 3 plus cosine square of 2 pi over 3, which will consequently come out with the final value being, we have square root 3 over 2 for sine of 2 pi over 3, and then here we square, and then we have 1/2 for cosine of 2 pi over 3. We square, added these two values together, so right hand and left hand side ultimately produce as a 3/4 plus a 1/4, which all adds up to be 1, and the right hand side consequently right hand side is permanently 1. And so once again, seeing that at this value of theta, we have the left hand side value turns out equals the right hand side, and we're going to roughly say, therefore, sine square plus cosine square theta equals 1. And we thought we found a proof for this identity. However, unfortunately, again, this is only an example. Because who knows if it works here in this example where we left theta equals 2 pi over 3, but at other value it's going to fail, and we don't have time to search for all different values out there. So this is not a proof. Alright, so now really let's prove an identity. So let me bring up one first proof right here. We would like to prove the identity, the trig identity. Cosine square theta over 1 plus sine theta equals 1 minus sine theta. So this problem here, we are about to prove that we want to show everyone who reads this, who views this video, we want to show everyone who learns about this identity that why this equality is always true regardless of which value we assign for theta from the two sides of your equality. And so to prove any identity here, there are two different styles. So allow me to prove the same problem here, but with two different styles, so that you can learn different techniques. And there are still many other styles out there that depending on people's creativity as well. But the point here now is that we need to prove why the equality now here is true without bringing in different values, so that we want to come up with a way to generally make it true, bring it out to light, regardless of which value we assign for the variable here. Okay, so now, so proving this identity, the more common style. So common style of this, of proving an identity, is to tackle down whichever side in your identity, whichever side in your equality has a more complicated or even just slightly more complicated expression, meaning it has more operations involved, it has more functions involved, it has a bigger expression. And that's what it's meant by being a complicated or slightly more complicated side. And so in this identity, I recognize that my left-hand side has more involved. And so, or in other words, the left-hand side is more complicated. And not always the left-hand side. So remember, the point here is that we looking for the side of your equality that has more things involved, that's more complicated. And so, now proving this identity, we are going to tackle down the side that's more complicated. So cosine square of theta over 1 plus sine of theta. The plan now is that we are going to algebraically or use your trig understanding to simplify it down, and that's the point. We pick the more complicated side to simplify it, so that we want to find out all the bridges, how it bridged from the left-hand side to eventually land into the right-hand side. And so cosine square of theta over 1 plus sine theta. So now, before attempting to reduce that, let's think about this a little bit. I introduced that a little while ago in other lessons and lectures about, now starting from our fundamental identity, even though we know that this is called a Pythagorean identity, but I will continue to call that the fundamental identity, because we can establish much more identities out of this. But so right from here we can rearrange that by subtracting sine square of theta from both sides. We can rearrange this as cosine square of theta will equals 1 minus sine square of theta. And I also mentioned a little bit briefly in some of our earlier lecture that this is also a quite useful identity. It's not big enough to deserve its own attention. However, people are using that quite commonly here. So cosine square can now be substituted by 1 minus sine square of theta. So we're bringing in those kind of understanding that anyone who view your proof can never argue about that. So why is it cosine square of theta equals 1 minus sine square theta? It's right here, and nobody can argue about that, and that's the point. But so here, currently at this step, we do not see anything that looks like the right-hand side yet, and that's the whole reason why we need to continue moving on and make a couple other steps, further steps. And so what I recognize now, and seems like I'm not doing anything with the bottom at all, with the denominator of our current fraction, and it's okay. It's all about trying to simplify the expression. So we take different routes for everybody. But how I see it here is 1 minus sine square can be regarded as a difference of 2 square. 1 can always be regarded as a 1 square, and sine square is perfectly already a square expression. So now, in other words, we can bring in that identity we've learned back in algebra. The difference of 2 squares can be thought of as the difference of 1 minus sine theta, but no square, and in product with 1 plus sine theta. And then the bottom, the denominator, remains the same. And so at this point here, algebraically, and still we do not see how this looks like the right-hand side. But so now algebra allows us to now cancel out the 1 plus sine theta away. 1 plus sine theta now can be canceled away. And so in our next step, this expression is reduced down to 1 minus sine of theta. And at this point, what we realized is that from a starting expression here, looking very complicated, we simplified it down. We did a couple substitution, and we simplified it down, and it is turned out equal to 1 minus sine theta. So now our bottom conclusion now is we can say, therefore, the left-hand side was the start, but now we did our deriving work, we did our simplification work, and we arrived down as cosine square of theta over 1 plus sine theta equals 1 minus sine theta. And this is the end of our proof right here, and we proved that completely based on the generality, the general understanding of trigonometry, instead of plugging in, substituting in different values of your angle theta. And so this is here where I call it the end of your proof right here. Now, this is just optional over here, but the tradition among the mathematicians that anytime you ending a proof right here, we put a huge period that's looking like a solid black square like that. But that's indicating we finished with our proof, and that's the end here. I'm going to prove a different trig identity where we can learn a different style in proving an identity, not as common as you have seen in the earlier part of this video, but it's also useful quite sometimes. let's say here we are going to prove the identity secant of theta minus cosine of theta, and we want to prove that it will always equals to sine of theta multiplied with in product with tangent of theta. So that other style I'm going to show in this example here, let's call it, it's just simply another style. Not as commonly used as the other style, but it does work sometimes. So here I am going to work out, in this style, I'm going to work out separately with my left hand side. So I'm going to produce a divider here so that it separates my working space into two separate columns here. So my left hand side being a secant theta minus cosine of theta. What we understand about secant theta is that it's the same as a definition, 1 over cosine theta. And so my left hand side expression now is turned into is 1 over cosine theta minus cosine theta. And so now we can do a little bit further algebra here, but making common denominator. So we're looking at our first term here as being 1 over cosine theta, but my second term it's essentially over 1, so we can make it cosine square theta over cosine theta. That's how we turn this. We can turn the second term into a cosine square theta over cosine theta. And so now that, as soon as we have common denominator here, we can bring the two terms into one fraction. So now I'm looking at 1 minus cosine square theta over cosine theta. And so we also learned further that 1 minus cosine theta has been known to be sine square theta and over cosine theta. So it seems like we didn't get anywhere too far yet. And so sometimes when we feel like we're stuck at this point, don't know how to simplify further, then we're going to turn our attention to over to the right hand side. So the right hand side, on the other hand, starting out with sine of theta multiplied with tangent theta. Tangent theta is always understood as sine theta over cosine theta. And so our starting expression here is the same as this ratio, sine theta over cosine theta multiplied with sine theta. And so algebraically, these two as a product becomes sine square theta over cosine theta. But now what have we reached here? What we have reached here is now the left hand side turns out to be sine square over cosine theta. The right hand side also, with a little bit of further development, we also turn that into a sine square over cosine theta. So what we notice now is the left hand side. So the left hand side, as we concluded here, the left hand side here, LHS stands for the left hand side expression, does come to agree with the right hand side, and that's what I meant by equal sign between the left hand side and the right hand side. And so now that's how we concluding our proof that so I'm going to say, therefore, our identity from the beginning, secant of theta minus cosine of theta on the left hand side will always equals to sine theta times tangent theta on the right hand side, regardless of which value we're substituting in for theta. And that is the end of our proof. Proving an identity is not only to prove it's true. From the most fundamental understanding of an identity, it is an equation. So a lot of time it's easy to mistake that an equation could be an identity. For example, something like this. sine of theta plus cosine of theta equals 1. It's an equation, but easy enough to mistakenly think that it could be an identity. So proving an identity, there are times that we actually need to prove it to be a false identity. And so in that case, we consider a problem like that as a disprove. And so let's learn how to disprove an identity. So disproving an identity is actually simpler than proving it. So, and remember again, the term disprove here means we're trying to prove this equation here claimed to be an identity, but we're trying to make it false actually. And so I'm just simply going to substitute in a value. So I'm going to let theta equals pi over 2. And so theta equals pi over 2 and substitute it in this equation for the variables, then what I see here is now we're going to have the left-hand side turns out to be sine of pi over 2 plus cosine of pi over 2. And the value here turns out to be sine of pi over 2 equals 1. And cosine of pi over 2 equals 0. Plus 0, we have a value 1. And the right-hand side turns out to be, has already been 1. And so at first, after seeing one quick example, we thought that sine of theta plus cosine of theta equals 1 is really true after looking at one example, but that's actually not the case. So we're finding in one example it worked, but let's find another one. This time we are going to pick a different example. How about let's let theta equals pi over 4. We tried with theta equals pi over 2 earlier and it worked. So let's say, what about pi equals pi over 4? We're going to repeat the same work right here. Let's substitute this value into the left-hand side, since the right-hand side doesn't even have a place for us to substitute the variable. And so left-hand side is going to produce left-hand side. So sine of pi over 4, substitute in for theta, plus cosine of, now substituting in for pi over 4 for theta. And that equals square root of 2 over 2 for sine, plus another square root of 2 over 2 for cosine. So this will consequently turns out to be, there are like terms. So we can combine like terms, and that turns out being 2 square root of 2 over 2, which reduces down to square root 2. And square root of 2 is actually approximately 1.414. So it's already not equal value with 1, which is the right-hand side. So now this equation at first thought to be an identity, but now when we try through one example when theta equals pi over 2, it worked. But now in a different example of the theta value at equals pi over 4, it did not work. And so this is actually a perfect proof for saying that sine of theta plus cosine of theta should not generally equals 1. And so in that case, our work here, our one example here that making the equation false right there is referred to as a counter example. Counter example. And as a different example, let's say we have sine value of an angle theta plus sine value of a different angle, let's say phi. So these are two different sine values of two different angles. So sine of theta and sine of phi. This is usually thought of as being the same or equal value with sine of, taking the sum of theta and phi. However, is this really true or not? It's actually now turned out not true. So how do we disprove this problem right here? So we can think about, I can come up with a counter example being theta being a pi over 2, and how about let phi equals pi over 3. And that means taking these two different values for the two variables, then my left hand side is going to be sine of pi over 2, as pi over 2 substituted in for theta, plus sine again of pi over 3, as pi over 3 is a different value substituted in for phi. And so let's now do the calculation. Sine of pi over 2 equals 1. Sine of pi over 3 equals a positive square root of 3 over 2. And then making denominator, we're going to end up with the left hand side being in exact expression 2 plus square root 3 over 2. The right hand side, let's find out. If we're now substituting both of these two values in place of the two variables on the right hand side, we're looking at something like this. Sine of, I'm going to open parentheses, brackets parentheses, and here I'm doing a pi over 2 plus a pi over 3. So my right hand side, working further on that, we're looking at sine of the sum of pi over 2 plus pi over 3, which in turn equals sine of 5 pi over 6. Because making common denominators and all that, and adding these two terms and bringing that into one fraction, pi over 2 plus pi over 3 should equals sine of 5 pi over 6. But sine of 5 pi over 6 is going to equal a positive 1/2. And so what I see now is that the left hand side turned out to be a value much greater than 1. But this right hand side is a value that's less than 1. So it cannot equal, or in other words, 2 plus square root 3 over 2 from the left hand side is not equal to the right hand side, 1/2. So in this case, once again, that implies that sine of theta plus sine of phi, some other angle, two different sine values on two different angles, they are not generally, or is not generally the same as sine on the sum of the two angles. That's how we disprove another thought to be identity. And so, and then here is again what we come up here, letting theta equals pi over 2 and letting phi equals pi over 3 is another counter example. And so after looking at how we prove or disprove an identity, then I have to make it clear that when a problem specifically asks you to prove an identity, the intention here is that it has already been known to be true. It just, the problem wants you to show you a step, making it true, showing it why it's true. A problem, on the other hand, that asks you to specifically disprove an identity, intentionally the identity has already been false. All you do is to come up with a counter example to find out how it's false. So let me make that bottom line right here. When the problem asks for proof, then the identity has been true. We just need to prove it. When the problem asks you to disprove, then the equation for identity has been false. And we just need to come up with a counterexample to really convince everybody, every reader, that it's false. The type of problem that is more dangerous here is that when you're given an equation and being asked to either prove or disprove. Say, for example, we have an equation, sine of theta equals square root of 1 minus cosine square theta, and we are being asked to prove, either prove or disprove. The intention of a problem like this is to indicate that simply looking at this equation right here, now nobody has a clue as whether or not this equation, this equality can be true regardless of any value for the input variable or not. So nobody knows. So that is now our responsibility to bring it out to light, that whether it could be true or it could not be true. And so that's why it's going to have to combine that skills of the proving skill or the disproving skill into something like this. Because like I said, we're starting out with something that we are completely clueless. We are completely unknown. We're starting out completely from scratch. All right, so here we go. Let's either find a way to disprove or prove. So having an equality given here, completely clueless whether it's true or not. Now, in my experience teaching throughout these years of teaching proving identities, here's how it would be wise of us here to start out here. Anytime you're starting out with an identity, with an equality from scratch, that you have no idea whether it could be true or not, regardless of the value, the different values, then it's better to find different examples first. We're going to try out a few different examples, maybe usually the 5 or 6. If it's going to be wrong, then one of those examples will run into a counter example. Then that's how we disprove it. And so here's how I work. I'm going to let theta equals a pi over 2. Okay. And so theta equals a pi over 2, then left hand side gives me sine of theta over 2 as we substitute it in for sine of pi over 2, as we substituted pi over 2 into theta, which in turn equals 1. Right hand side we have 1 minus cosine square of theta. I should have now written cosine square of pi over 2 as we already substituted pi over 2 in place of theta. And we take an overall square root. So I purposely wrote the expression that involves order of operation. And so this in turn will equals 1 minus. Now cosine of pi over 2 is a 0, so cosine square is also a 0. So inside the square root, we're looking at just simply 1. So square root of 1 equals 1. So for this first example we chose, we found the left-hand side equals the right-hand side. But that doesn't mean truly this sine theta equals square root of 1 minus cosine square. Just because one example worked. As I already explained when we were learning how to prove. And so finding one example worked. We have to search for another example, because who knows, there are the other examples out there that immediately make it false. As a different example, let's pick theta equals 5 pi over 4. And the way it works is very similar to how it worked with the earlier example. So now when theta equals 5 pi over 4, then left-hand side gives me sine of 5 pi over 4, which in turn equals, this is going to be a negative square root 2 over 2. Remind yourself that 5 pi over 4 is the angle that belongs to the third quadrant. So the y value there is a negative value. And then we're done with the left-hand side. The right-hand side, on the other hand, and of course it's the other hand, we're looking at 1 minus cosine square of 5 pi over 4. And we take square root. But in turn, cosine of 5 pi over 4 is the same as another negative square root 2 over 2. But here in our expressions, we square that including the sine. And so that will come out being another square root, 1 minus, consequently result in this minus, but the other minus inside the square here gets squared up and become positive. So here negative square root of 2 over 2, but square will become a 1/2. And 1 minus 1/2 inside the square root will give us a positive 1/2 inside the square root. And taking this positive square root actually gives me a positive square root 2 over 2. And so what it turns out now is that we found a counterexample for this equation, this equality thought to be an identity, but it's now turned out it's not. Left-hand side is this negative square root 2 over 2. Right-hand side is the square root of 2 over 2. And so these two values from the left-hand side and the right-hand side are obviously not equal. And so what we just did here is a disprove. Generally, that implies that our final conclusion, generally sine of theta is not equal to square root of 1 minus cosine of theta. And what we did here, we disproved, it was a disproved the problem. And we found two examples. The first one worked and the second one failed, making our equality here failed. And so this value right here that we chose is regarded as a, once again, the term for that, counter example. And here is another example of trying to either prove or disprove. So we want to prove or disprove. And the equality thought to be an identity is like this. We have a tangent of theta times cosine of theta. And that equals sine theta. And so with something like this, and like I said, from scratch, we can pick a value. Say, let theta equals a pi over 4. And so left-hand side quickly give me tangent of pi over 4 times cosine pi over 4 should equals on the left hand side, this is 1 for tangent of pi over 4. This is cosine of pi over 4 being a square root 2 over 2. So 1 times square root 2 over 2, which in turn equals to square root 2 over 2. Right hand side is a separate calculation. Sine of pi over 4 substituted for theta, and that is equals to square root 2 over 2. So first example we picked, it worked. So this is not a counter example. And then we try theta equals, let's say, 5 pi over 6. And so on the right hand side, on the left hand side, we're looking at tangent of 5 pi over 6 multiplied with cosine of 5 pi over 6. And so now we have done these basic evaluation problems long enough, so I'm leaving the calculation for you. Go ahead and pause the video and take a minute or so to do the calculation. The final value on the left hand side should come out to be a 1/2. And right hand side, we're going to have a setup sine of 5 pi over 6 as I substituted 5 pi over 6 into my place of theta. And that also equals 1/2. So our second example where we specifically assign a value for theta, it worked again. Left hand side equals right hand side. So usually I would go with about 5 attempts, making it false. But if after 5 attempts are all unsuccessful, we're going to start looking for a way to prove it. And so why don't you pause the video and try about a few more attempts right here, choosing different other values of theta, and then come back and we're going to see whether we should prove it. All right, so welcome back. And so I highly believe that you should have tried about 3 or 4 more attempts to disprove this by looking for some counterexample, but I highly believe that all of your attempts there when you pause the video should have all been the left hand side equals the right hand side. And so in that way, so now we're going to think, hey, maybe we should find a way to solidly prove the validity of this identity right here. And so let's stay with that common style of proving the identity. The left hand side seems to have more things involved, slightly more complicated. So I'm going to go ahead and going to start out with my left hand side. Tangent of theta times cosine of theta, famously known to be tangent of theta, is famously known as a definition, sine of theta over cosine theta. So we are bringing up an understanding or information that nobody can argue with us on that. And then we multiply this fraction with cosine of theta, because that's how it was from the left hand side. And so now algebraically, we can just simply see that, hey, cosine of theta appears to be the common factor. So we can cancel out, and that equals sine of theta. And so now we just made the bridge, the connection. And every step that we move here, once again, nobody can argue with us here, as we brought up information that we brought up, understanding that that's common to everybody. And so now we actually prove this. Equality now becomes an identity. It's true regardless of any value of theta. So in other words, final conclusion. So tangent, therefore, tangent theta times cosine theta equals sine of theta. And we end the proof here.